Thank you. Hello, participants. Thanks for the hearts. I am going to now send out a link for a board that will be shared between Brandon and myself. It's an online board that's called Fox, and anyone can collaborate on it. It's a very nice, free actually tool that everybody can use. And I'm late. I'm sorry for that. I should have prepared this before 11 o'clock. And here is the link, Brendan. I'm going to paste the link in the chat here for you. I'm almost there.
Got it.
And what I'm going to do now is share the screen for everybody. Okay, sharing the screen. Can everybody see the screen? Can you please confirm in the chat if you can see the screen? Hi, Kaden. I see you wrote your grade 8. You're very welcome. If you have watched yesterday's session, then you should be all right. We are going to build on what we did yesterday. If you haven't watched yesterday's session, it might be a little bit challenging, but you might still want to stay on until you are fine. Shall we test, Brendan, if we can both?
Yes, let's do that. I think it's a good idea.
Maybe we can use different colors so we can distinguish who writes what. Which color would you like to use, Brendan?
I'll use the blue, the dark blue.
All right, I'm going to use then the black. Is my scribble showing on your side?
I can see your scribble. My scribble, on the other hand, is not scribbling. Let me just find out why.
Not working?
No, I have all the tools on the screen, but I don't seem to be allowed to use any of them.
Really? Okay. Let me see if I shared it correctly. Maybe I didn't do it correctly. Let me quickly fix that.
All right.
Apologies, everybody. That's really strange. Maybe we can then, shall we just use my board then?
Let's use yours. Yeah, I'll keep an eye on the chat for you.
Thank you very much.
Yes, it's open to anyone in high school. You don't have to worry if you're in grade 8. It's no problem. I mean, really, it's open to anyone.
All right, so I'm sharing now a different board, which only I can draw on. And could you please confirm if you can see what I'm writing right now? on Zoom?
They should be able to. Lots of thumbs up.
Fantastic. We've got two sets here, A and B. And let's quickly recall on the example of these two sets, what is going to be their union. Oh, by the way, Brendan, we didn't discuss what we're going to be talking about. Do you have some suggestions?
I think union and intersection. We didn't actually talk about the element of relation yesterday. I feel that should be mentioned.
You know what? Let me tell you what I was thinking about. So we introduced two symbols yesterday. This was the subset relation symbol.
Yes, we should definitely spend some time on that.
And we also introduced the symbol of union. And I was thinking, maybe we can do some actual algebra with these two things, like
sure.
deriving algebraic properties. It will also kind of explain why these lectures are called abstract algebra lectures.
Good, let's do that.
All right, those who are in the audience. Okay, so Lesedi says that they were not here yesterday. That's okay. Try to catch up still what we're doing. We're going to be revising a little bit of what we did, and let's see if it works for you.
And you can also watch yesterday's session on YouTube as well.
Afterwards, yeah. So if A equals the set consisting of 1, 2, 3, and B equals the set consisting of 3 and 4, what would be the elements of the union of A and B? One, two. So we got there. One of the answers there is 1, 2, 3, 3, 4. Let me write it down. And one of the things we discussed yesterday is that when we have a repetition, it doesn't really count because two identical copies of 3 are still going to be the same 3. So we might just as well write it once. Do you agree with that, Brendan?
I do. If you want a nice example where you've seen this come up, think about, chat, what happens on a computer when you merge two folders together, right? You get that little pop-up that says, would you like to replace the duplicates? So if you put two folders together on a computer and you take away the duplicates, that's a bit like taking a union.
Right. Would you like to remind everybody the intuition of the union and terminology while I'm writing this out? For instance, for those who are not who were not here yesterday.
Okay, so if I've got two collections of things, so we had two sets of numbers. I want to think about different ways that I can put these collections together. And this first type of bringing together we see has been called the union because it unifies these two collections. So a nice physical way of thinking about this is I've got two boxes of objects. I want to put them all into the same box. Well, the easiest way to do that is to just pour the one box into the other box. But we remove the duplicates. So we only show one copy of each distinct object, but the idea is here that I'm going to take these two boxes and I'm simply going to combine their contents in maybe the most intuitive way, which is just to pour them together. So it's a way that we can, in some sense, add two sets together.
So I'm illustrating what you're saying, Brendan. If we have here 1, 2, and 3 in the box A, and we have 3 and 4 in box B, then in the union we'll have everything that was in A, as well as everything that's in D. And if there is a repetition, it just
write it
means
down.
that the same, yeah. Of course, in real life, you cannot have two different boxes with the same object residing in each of them in this at the same time. But you could have that the box A was formed yesterday and the box B will be formed tomorrow, and then the same object can appear in both A and B at the same, not at the same time, but still at the same time in a different way.
Can we scroll up slightly, Zurab? Some of them just want to look at your paragraph again.
Yeah, let's do that. Good so far.
So is this clear for everyone? What this operation, what this procedure does of combining these two sets together?
Fantastic. And the other thing that will be relevant for the discussion now is this concept of the empty set. That's when the box is empty. Let me call it a different name, C. Here's another symbol for it. And now we have a certain analogy. We have a kind of analogy with numbers. It's only going to be an analogy. Don't think of this as a direct correspondence. I want to draw this analogy because I want us to look into the algebra of sets, which will, because of the analogy, look similar to the algebra of numbers. So here's the analogy I have in mind. So on this side, we've got sets. On that side, we've got numbers. First of all, notation. Numbers we denote like this: 0, 1, 2, 3, and so on. For sets, we have this container notation, right? And then inside the set, I can have numbers or other objects as well. I can have a set, for instance, with 1, 2, and an apple inside. And so on. And then we use letters for representing these sets, giving them names, just as a shorthand notation. Like, for instance, A could be the set of 3 and 4. We also use letters sometimes for numbers when we want to solve an equation, for instance. We could say x equals 5. Then we can compare numbers with inequality. We can say 1 is lesser or equal to 2, or 5 is greater or equal to 4. Actually, I'm only going to stick with the first one. We could say also 0 is less or equal to 10. So this ability to compare numbers is kind of similar to what, Brendan? I'm confused. Now suddenly I'm lost. I don't know what I'm talking about.
I would say it's similar to the idea of
wait, sorry. Maybe somebody.
Should we let them try?
Yeah, maybe they can tell us. Maybe they can. What would you think would be similar to comparison of numbers in terms of one being less than the other on the side of sets? Any thoughts on that? How can we compare sets? Did we learn a way to compare two sets? Well, we can compare them if they're equal, and that would be similar to equality of numbers. We can say 5 equals 2 plus 3, for instance. And on the left side, we could say the set having 1 and 2 in it equals the union of the set having 1 in it and the set having 2 in it. But that's that comparison the analog of that comparison for numbers is actually equality of numbers. What would be an analog for less or equal for numbers? Fantastic. We've got a very interesting answer here. If a set is a subset of another set, it is less than or equal to that set in that sense, in some sense. And we can also compare sets by the number of their elements. We'll be kind of cheating, because if we compare sets by the number of the elements, it's a bit like going on in the other side by counting how many there are and then comparing them as numbers. We want something very distinctive on the left side. So I'm going to stick with the subset relation comparison. Like the set consisting of 5 and 10 is a subset of the set consisting of 5, 10, and an elephant. So we have less or equal for numbers. For sets, we have subset. We have equality for numbers. For sets, we have also equality, something that's analogous to that. And then one final thing I want to draw in this analogy table is addition, which would be analogous to, while I draw that, maybe you can tell me what it will analogous to. So we can create a new number out of 2 and 3 by adding them. Do we have an analogous way of creating a new set?
What do we think, everybody?
Okay, there is an answer yes. So would you like to suggest what is it? Union, that's right. That's all we discussed, subset relation and the union of two sets. So kind of makes sense that we want to look at that. We could form a union of two sets, let's say, by taking set having just 1 in it and a set having just 2 in it, and then taking their union, which will be the set having both 1 and 2 in it.
But I think it's important to add here, remember, it is just an analogy. We're not actually going to add the numbers, the elements 1 and 2 together in the union. So that's
right.
not going to become the set containing 3.
No,
the set,
no.
Yeah.
It's just an analogy. You cannot really work out what's going on the left side by knowing what's going on the right side. You cannot work out, let's say, subset in terms of less or equal, and you cannot work out union in terms of addition. But interestingly, you can work these things out if you take this as your fundamental knowledge. We are not going to go into that now, however. I think, what do you think, Brendan? Shall we leave that for some future exploration?
I agree. Yes.
Instead, what I was trying to suggest that we do is to, sorry that my blackboard suddenly became smaller for me to be able to extend it. We're going to do some algebra with these 3 things, with the equality, the union, and the subset relation, which will resemble a lot algebra for addition of numbers. Okay, so what's the most basic fact in algebra which involves addition of numbers? Any takes on that? Can you state some very, very basic fact that involves addition of numbers? Like, what would be the most basic fact? X plus Y equals Y plus X. What a wonderful and beautiful rule is that.
Fantastic place to start.
Yeah, absolutely. Yeah, this is like such a useful rule. X plus Y equals Y plus X. It is very important applications. Why does it have important applications? Well, here's one important application. Imagine somebody is offering you 2 bags of money. One contains
About the noise.
1 million rands or dollars, and the other contains $2 million. But they're heavy. You cannot take both of them at the same time. So you have to take one and then the other. Now, you need to be very clever to decide which one to take first so that you actually get the same amount of money and the money doesn't decrease. But guess what? It doesn't matter in which order you grab this money. If you grab it this way, or you grab it the other way, you first take the other one and then the first one, you'll still end up with the same amount of money. And that's thanks to this rule. So when somebody is offering you 2 bags of money, don't worry about the order you take it. You can take randomly one and then the other. You'll still end up with the same amount of money. We have a nice comment here. By the way, maybe I should introduce you to. So we've got Amy and Olinda joining here from my office. I'm going to show the background so you can see them.
Hi everyone.
Hello, hello.
I'm saying I will take the amount with the bag with the bigger amount first, in case I don't have a chance to go back and take the other one.
Yeah, that's a very good suggestion. Okay, so let's look at an analog of this rule, which is rule for addition of numbers. With union. So what would I write here? Brendan, would you like to suggest to me what I should write here? How do I even write down an analog of something like this with union?
Well, instead of numbers, we would need 2 sets to start with. So
can I call them?
shall we use them capital letters for the sets?
Okay, let's do that. So A and B. So I'm using A in the place of X and using B in the place of Y.
And now we said before that our analog for addition is the union.
So should I put union in the place of plus?
Seems
Okay.
like it.
Oh, we've got a hint there on the. Thanks very much, Wazi. You helped me a lot. So that's what it says in chat, and I'm in full agreement. There is a nice correspondence here. Equality stays equality according to our analogy table. That's how it should work. Plus switches to union, and then we've got this rule now. But how do we know this is still true? We don't know that yet, right? We have to establish this first. We're kind of exploring the arithmetic of sets for the first time, and we cannot just write rules down. We have to check that they actually work. How are we going to do that? Does anyone want to explain? Maybe turn on your microphone and maybe even camera if you want to, and explain what you think. Will this rule be correct or not? And if yes, then explain to us why do you think it will be correct?
You have a hand. Would you like to tell us in words?
I would like to say it's incorrect because there is no plus indicating that the letters are equal to each other.
If they're equal to each other, we get A union A equals A union A, right?
Yes.
And is that incorrect?
It is correct.
Okay, in this case, it's correct. And if they're not equal, you think it's going to be incorrect?
Yes.
What makes you think so?
Okay, it's not about the positioning of the words, of the letters, I mean, but but I see no pluses, just like the first one.
So let's look at an example. Let's say our A and B are the sets 1, 2, and so that's A, and B is the
Yes.
set 2, 3.
We get fun.
When we take their union, we're going to get which set?
Yes.
Which set do you think we're going to get when we take the union of these two sets?
Please come again.
So if A is the set having 1 and 2 in it, and B is the set having 2 and 3 in it, and we take their
Yes.
union, which set do you think we're going to get?
Which 1, 2, 3.
I agree.
Because of
I agree. We're going to get 1, 2, 3. I agree. Now,
Yes.
if we now, so this is like the left-hand side, right? We worked out the left-hand side of the equality. Now,
Yes.
let's look at the right-hand side of the equality. So that would be the other way around. So 2, 3, union
Yes.
with 1, 2. And what set do we get in this case?
1, 2, 3 again, I guess.
Well, if we get 1, 2, 3 again, doesn't that mean that in this example at least, these two things are equal?
Yes. Oh, I see it now. Thank you.
Okay, great. Thank you very much.
Good, thank you.
The way that I personally would solve and prove it to be true is I would say that for contradiction's sake, they aren't equal. Then you would do a base case, for example, like the one you just did there, in which you would prove that they are equal, meaning that the statement is false, meaning that they have to be equal.
Okay, that's an interesting way of thinking about it. So if we follow your line of thought, we can say that if they're not equal, then one of them will have an element that the other one doesn't, right? That's what it means for sets not to be equal.
Same elements.
Okay, let's rather say it like that. Thanks, Naluntu.
Yeah.
So then this and that will not have exactly same elements. But elements of A union B are elements of A combined with elements of B. The same is true for B union A. That also combines elements of B and elements of A together, right? So we get a contradiction. And hence, they need to equal each other. Now, one remark I would make, so first of all, did I, was it UK?
Yes.
Yeah, so is this what you were thinking of?
Yes.
Okay, I just want to make one remark here. I think it wasn't really necessary to go into contradiction here, because if I just delete some of what I wrote, let's say I just delete this part, this whole thing I delete, and I just explain by saying elements of A union B are elements of A combined with elements of B. The same is true for B union A, and then I delete the conclusion. Isn't this already explaining to me that the two sets actually will have to be equal to each other.
Yes, it would.
Yeah. So we don't actually need to use this technique of contradiction. And now let's also look at what we've got in the chat.
Yes, there's some nice observations there.
So Jenna is saying that the two sets will equal because combining two sets in any order will result in having the same elements in the unified set, just in a different order, which can be rearranged to be the same order, showing that they're equal. Yeah, that's a wonderful explanation. That's very intuitive. And then we also have another comment here. If you're creating a union of two sets, the order in which you add the sets together doesn't matter. Using the analogy of the boxes, the order in which you place the items in the box does not make a difference because the same items will still end up in the box. I completely agree with that as well.
Very nice.
Yeah.
So it seems like we have different ways of understanding this, but all of them seem to give us the same understanding, namely that this rule that we had for addition, where the order in which we combine things doesn't matter, also works for union. So let's write this out one more time. We can now say that A union B equals B union A. And when we establish a mathematical fact, we can call it a proposition. A mathematical proposition is a statement of some fact. Here we have another explanation in the chat from Sebastian. Because the two sets are subsets of each other, they must be equal. This is yet another way to explain this. And I would actually like to spell that out a little bit. So what is a proof in mathematics? Well, a proof is just an explanation that shows us why something works. But before I go ahead, maybe I should unmute. So Unami, you want to add something to this?
Sorry, so I wasn't listening. Can you please repeat what you wanted me to confirm?
No, I just saw that you had your hand up, so I was wondering if you wanted to say something.
Oh no, I forgot to take it down.
Okay, great, thanks. So I'm going to follow Sebastian's suggestion here in the chat, using the subset relationship to get the equality. We can say, we can pick an element in the left-hand side set. So let's say that x be an element in A union B. Okay, somebody's worried. I saw worried faces are coming up. So what are you worried about? Did I do something bad? Is this too many words? We shouldn't maybe go into so many words. We can be happy with the intuitive explanation that we gave earlier. Brendan, what do you think? What did I do bad here?
Well, you said the word proof. Maybe that scared them.
Okay, but somebody still likes to know the proof. So
someone wants to know.
Look at it.
So.
Yeah. So let X be an element in A union B. Then
maybe it would be a good idea to first tell them what your approach is going to be before we
yeah.
write it down.
So the approach is the one that Sebastian told us, that we will show that A union B is a subset of B union A. Maybe you're actually right, Brendan. Maybe let's actually write this out.
Yeah, let's sort of give them a strategy, I think.
Yeah. We will show that on one hand, A union B is a subset of B union A, and also that B union A is a subset of A union B. If we show that these two sets are subsets of each other, then there will be the same set, because being subset means that everything in one is in the other, and also the other subset means everything in the other is in the first one. So then they must have the same elements.
And maybe we should tell them, how do we show one set as a subset of another?
This would show that the two sets are equal if we show that they are subsets of each other. Okay, I'm going to now answer that request of yours, Brendan. So how are we going to show that, let's say, A union B is a subset of B union A? Okay. We will show, yeah, somebody want to say something? Bonami, did you want to say something?
I think he just forgot to mute.
So we will show that A union B is a subset of B union A by showing that every element of A union B is also an element of B union A. Does that make sense so far? Did this answer your question, your request, Brendan? Okay, we've got a few thumbs up. That's great. Yeah.
So another way to think about this chat is to say that we're going to show everything in the set on the left of the subset symbol is in the set on the right of the subset symbol.
Yeah, everything in
there is in there.
Yeah. That's what we're going to show. Everything here is in there. That's what it means to be subset. Okay. So now we need to actually show that, right? So we have to pick an element in here, analyze what properties it would have, then to be able to conclude that it's also in there. So let's pick an element. Let X be, just give it a random name, X. Let X be an element of A union B. Then, if something is a union of two sets, what can we say about that? Union means combining together, right? If I've got something in the combination, then that thing will have to be either in one or the other, right? So then X is an element of A, or it is an element of B, either one or the other.
Are we okay with that, everyone?
I see a thumbs up going, so maybe it means yes.
Okay, good.
But if X is either in one or the other, that also is the same as to say that it's either in the other or the first, right? The order in which we put the or, the order in which we combine statements with or doesn't really matter, right? It could also be in both.
Yes.
It's fine if it's in both, as long as it's in at least one of them. So we could also then say, we could also then say that X is in B or in A. I just switch them around, because when we say or, it doesn't matter in which order we say two things, right? But if X is in B or in A, it means that it's in the combination of B and A. So X is an element in B union A, which is exactly what we wanted, right? We wanted to show that if I've got a random element of A union B, it will end up being an element of B union A as well. Is that good? Does that make sense, everyone?
So physically what's happened here is we've taken a box A and a box B, we've poured them together into a big box. Then I've reached into this box and I've pulled out an object called X. And I'm asking, does it matter which box he came from and in which order did he come from? Right? Once they're combined together, it doesn't really matter which part of the pile he's from.
And that's a nice, I really like that explanation. Let me make an illustration for that. So the words we're writing out here has a very nice illustration in real world. So we had these two boxes, A and B. We formed their union, A union B, by first putting the contents of A in this bigger box, and after that, putting the contents of B in the bigger box. Now, once we finished that, we picked out a random element X from that union. So that X will have to come, because there was nothing else added to this box, so it will have to come either from that box or the other one. And so if the order was different, if we first emptied the B box into the big one and then the A box into the big one, this X would still be there.
Yeah.
Because if X comes from A, then it would be there because of A. If it comes from B, it will be there because of B.
Sure.
We could kind of break this down into more steps if we wanted to, if we were not satisfied. But I think we are satisfied, so we can move on with the proof. Now, we've shown this way that A union B is a subset of B union A, but it doesn't really matter what is called A and B, right? We could have done exactly the same discussion to show that B union A is a subset of A union B. Would have been exactly the same, right? So we can just say, we can be lazy a little bit and just say, in a similar way, we could show that B union A is a subset of A union B, which then proves, now that we've shown both of these, this proves that A union B equals B union A.
And the analog there physically, if you look at that pink sketch, if you just relabel the boxes A and B in the other order, you should see we're doing the same thing again.
Yeah. So intuitively, it's also quite obvious that the order in which we empty box will not affect the contents of the bigger box. Well, we kind of promised to do algebra, and we ended up doing logic. This is logic.
Yeah.
This is logic here. What we did here is logic. We're not going to do more logic today. This is just a little glimpse of what can come later when we will have sessions on abstract logic, or logic rather. What we want to do is to do algebra. Now, we needed the logic to establish an algebraic law. We can now think of this as a law that is valid for union of sets. And we want other laws as well. Let's establish these other laws in an intuitive way. Let's not break them down using logic as we did now, not to mix up everything together at once. And then let's see what kind of algebraic manipulations we can perform thanks to these laws. There was already another law that was suggested for union. That was suggested a while back. Do you remember, Brandon, if you saw that one?
It was
Sebastian
yes.
suggested the other one, yeah. So another fact we know about numbers is that the way we put brackets when we add numbers doesn't matter. So if I add numbers y, z first, and then on the left to that I add x, it's the same as adding x and y first, and on the right adding z. We all know that, right? Let's work out what will be an analog of this for union. I forgot how to do this. Can someone remind me? Can we transport this law and turn it by the analogy table we had before? Can we somehow turn this into a law for union? Any ideas? Everybody's silent. I wonder if there are further questions or queries about this proof and the proposition we had.
They have
Brendan,
gone
you
very
can
quiet.
still hear me, right?
Yes, yes, we're still on.
Okay.
Can chat thumbs up. They can. Oh no, there we are. They're back.
Okay,
have some
okay,
suggestions.
okay, great. Yeah, no, I like these suggestions. They look very natural. Okay, let's write them out. They're both the same, I think. A union B union C equaling A union B union C. And we've got another one there from Lazi, which is the same rule, but with X, Y, and Z in the place of A, B, C. That's all very good. Of course, the naming of the letters doesn't really matter. Let's make sense of this rule. Maybe with, instead of boxes, let's use the kind of diagrams that were used yesterday, the thing called Venn diagram. So let's imagine this is A. So there are some entities here in A, some elements, okay? And let's say this is B. And we draw it in such a way as to also take into account that there might be something in the overlap of the two. And we now, maybe there is more than just two of them there. Okay, we've got some surprise faces there. So let's make a concrete example out of this. A could be a set having elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So let's write them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And B could be a set having elements 6, 7, 8, 9, 10, and then 11, 12, 13, 14, 15, 16. So let's write that out. 6, 7, 8. I'm just going to be a bit lazy here. All the numbers from 8 all the way up to 16. And let's draw a C there. Maybe C will be something like this.
This intersection.
17, 18, 19. So what are the elements of C? Let's write them out carefully. So 4 is there, 5 is there, 10 is there, 9 is there as well, 10 is there, 11, 12, 17, 18, 19. Right?
Yeah.
Mm-hmm.
Okay. Now we're going to use this picture to calculate what are elements of the left-hand side set and what are the elements of the right-hand side set, and see if we get the same answer. Gonna make it a bit smaller and then copy it second time. So let's start calculating on the picture the left-hand side. What do I calculate first? If I want to calculate this expression, what do I do first in my as a first step in my calculation? Yeah, that's a good suggestion. Find B union C. So let's find B union C. This is B, and that's C. And B union C is putting the two sets together, right?
Yeah.
So I think B union C will be everything that goes in this shaded area I'm going to draw. So this is the shaded area for C, and this needs to be combined with the shaded area for B. So that's B union C. Everything that falls in that yellow area will be B union C. We all agree on that.
Yeah.
Now that we formed B union C, let's combine that in a union with A. So I need to now put together this yellow shaded area and the A. And so that means I need to shade A as well. So that's the answer for A union B union C. What about the answer for the other expression, A union B union C?
What should we do first here?
Which one do I do first here? To calculate this, what do I do first? I agree. I agree. Thank you very much for the suggestions in the chat. We first work out A union B.
So just like with arithmetic with numbers, the brackets here are giving you an order of operation. So there's an analogous relationship there as well.
Right. So we do A union B first. So we shade A and then we shade B. Or we could have also done the other way around. We know now that it doesn't really matter which order we do that. So here is A union B. And we've got this so far. And now I want to combine that with C. Right? And so we get the same picture, don't we? In both cases, all three of them got to be put together. So these two things, we can see in this example at least, they're equal.
True.
Is this clear for everyone?
I have a question for our audience.
Yes.
Did it matter what numbers we put in our example?
That's a good question. We've got an answer there. It didn't
Lots of
matter.
no's. So do we feel like this will always work? It doesn't really matter which A, B, and C we choose.
We kind of didn't really do anything with those numbers in the end, right?
No, we just scratched over them. They could have been anything. They didn't even need to be numbers.
Yeah. So we have another proposition here. Proposition. This is equal to the other one. In the case of the law A union B equals B union A, we gave an intuitive understanding why that should be true, and we also gave a logical proof of that in words, right? And we said that we're not going to give a proof in words for this rule, for this law. Instead, what I would like to do is to invite you, those who are listening here, to write up your own proof and send it to us. We'll be keen to look at it and maybe even give you some feedback. Unless we receive 100,000 submissions, then we might struggle to give you timely feedback. Write your own proof and send to. So, are you also happy, Brandon, to receive some of the proofs in your mailbox?
Absolutely, sure, no problem.
Remind me your email address, please.
It's blang at sun. Yes, that one.
And my email address is zurab@sun.ac.za. So you can send any of these two addresses.
We have an interesting question in the chat.
Let's look at that. Does it matter if A union B is considered and C, which is not included, has similar elements? Do you understand this question, Brandon?
I'm not completely sure, George. When you say similar elements, can you tell us some more? Do you want to talk?
Can you hear me?
Yes.
Okay, I'm just wondering for the proof if there's any contradiction there.
But the case that you're looking at, that's the one we don't understand. So what case are you thinking that could cause a contradiction? Okay, so thanks everybody for joining back. Those who have, we definitely lost around 30 participants in the process. We had a technical problem. Sorry about this. And we should maybe continue, Brendan. What do you think?
I think so. We still got half an hour.
And the recording is on, right? You can see on your
Yes,
side.
it's already recording.
Fantastic. So we stopped at this point where we wrote down the email addresses to which you can send your own proof of this proposition. We did work out that this equality holds on an example. The example was kind of general enough. We are quite firmly convinced that it should always work. Would be good if we can test this conviction by setting up a logical proof, just like similar to the one we did for the other proposition. So if you'd like to do that in your own time and send us your proof, please go ahead. We'll be very keen to look at your proof. And what we're going to do now is to move on with the algebra of union. So we already have two laws we've established for union. And maybe already with those two, we can play around a little bit and do a bit of algebra. So I'm going to write two complicated expressions, and let's see if we can check whether they are representing the same set or not by applying those laws we just established. Here is the first complicated expression. you see my expression is very complicated. And I want that to be equal to this. And I want to establish this equality in an algebraic way where we apply the two rules we learned. We established, in fact, not just learn, but we even understand why they must be true. The first being that if you take two sets and you take their union, I'm deliberately using different letters now, not to confuse with the letters we're given in this specific case, then the order in which we take their union doesn't matter. And the other rule is that the arrangement of brackets also doesn't matter. So we have these two rules, and using them, we want to get to this complicated expression here being equal to that complicated expression. Brendan, do you have on your side ability to share like thumbs up and all these icons?
We should do. Yes, there.
Okay, fantastic.
Did that work?
Yeah. Thank you, and thanks also to Sebastian. So how can we get from here? How can we get that to equal to the other one? Well, I mean, if we look at this, if we don't mind the brackets and also the order in which the sets are unioned together, we've got there in each case, in the top one and the bottom one, we've got A, B, C, D, E, right? So in the top one we have A, B, C, D, E. Here's A, here's B, here's C, here's D, here's E. And the bottom one we also have A, B, C, D, E. Here's A, here's B, here's C, here's D, here's E. And we want to see whether these two expressions will be equal to each other by using those two rules that we know this is true in general. Lebogang says he can't hear anything. Everybody else can hear, right? It might be a problem on your side, Lebogang. Sorry about that.
Yes, I think so.
You might want to disconnect and reconnect again. Maybe I'll write. So I'm writing now for Lebogang because maybe can you do that, Brendan, please? Can you respond to it in the chat because he can't hear us, so he can't hear.
True. Yeah.
The suggestion, yeah, we gave him, yeah. Okay, so we could use the first rule. So let's now look at this carefully. We can use the first rule to swap around the order of E and this big thing here. If I think of this E as being my Y and this being X, then the order in which we take their union according to the first rule doesn't matter. So we can swap them around. So in my second line, I'm going to write that equals E union that whole big thing.
Wow.
So I've already made some progress because at the end, I want to get to E union with something, and I've already got E union with something. Now I just want this thing to match with the other one. It seems like Lebogang still cannot hear us. What about others? Does anyone else hear us? If you can hear us, can you maybe put your thumbs up? Thanks. So what do you think we should do next? So we've got this, and now I want to manipulate inside here to get it to look similar to what we've got here. Notice that A, in both cases, is on the left side. But the inconvenient thing is that here we've got brackets around A union B, and there A is standing outside of those brackets. So maybe we can use the second rule, which allows me to have something that's inside the brackets on the left side, like X union Y, and shift those brackets to the right side on the left side of the equality there. So if I think of my A to be X, and I think of my B to be Y, and I think of the C union D to be Z, then with this way of thinking about them, I can write that A union B union C union D equals A union open bracket B union open bracket C union D. And that's exactly what Sebastian suggested. Thank you very much, Sebastian, for that suggestion.
So do we understand the first two steps?
In the first step, we are swapping the order of E and that by applying the first rule. And in the second step, we are shifting this pair of brackets from left to right. They have been shifted there by applying the second rule. Now, what we have here looks even more similar to where we want to get to. We just need to work out this thing inside there being equal to that. The B is on the wrong side, the C is in the middle, and the D is on the wrong side as well. So maybe to get them on the right side.
Let's let them suggest a step, I think.
Who's suggesting a step?
No, I'm saying let's see what they think we should do next.
Oh, that's a good idea, yeah. What step would you suggest as the next step to try to come closer to our destination here? I would imagine we keep these intact, the E and the A stay the same, and then what do we do? What kind of manipulation do we do inside with this expression? Any suggestions there? While you're thinking, let's write down what we would get if we applied each of these two rules. If we applied the first rule of swapping around the union, we could either apply for this union or for that one. If we applied it for this union, we would get C union D, union B. If we applied for the second one, we would get B union D union C. Okay, this is if we use the first rule. If, on the other hand, we use the second rule, this rule, then in this expression, I could move my brackets from there to the left. So I could have it as B union C, union D. So these are basically our options at this stage. Which of these three options shall we use? And there is already a suggestion I see.
So we're going to use the second rule.
And the suggestion is to use the third option, right?
Yeah.
So using the second rule. Is it going to be helpful? Perhaps. So we'll have B union C union with D. Okay, what do we do next? Then use the first rule twice. There's a suggestion there. It's an interesting suggestion. So if I use it once, I could maybe use it for the inside part. Then I'll get C union B, union D. It's actually nice because now this is in the same order as I had here. And if I use it the second time, it will swap these two around, which is exactly what we have here. And so we are done. Is everybody fine with this? Fantastic.
I think it's interesting to note here that these sort of manipulations are something that we're very comfortable to do with numbers. But here we're showing you can actually do them with a completely new kind of object, right? I mean, we're not working with numbers anymore. But we've created this nice set of rules that lets you do manipulation as though this were numbers. So we're coming back to that analogy table we started with.
Indeed, yeah, absolutely. Very interesting that we seem to be doing something very similar to what we're used to, algebra, but now we're not doing algebra anymore with numbers, we're doing algebra with sets. Okay. There are more rules that I would like us to establish, and these ones are going to be surprising because they're going to be slightly different to what we know for addition. Specifically, one I have in mind is the following. I'm just trying to make more space for the board. What happens when we do A union A? Can this simplify? Can A union A simplify? Somebody wrote something in the chat that it equals A. If I put the contents of A together with the contents of A, I will just get those elements duplicated, but duplication then doesn't change anything, so I will just get the same A. And this is something that if we look at the analog for addition, it will be very false, because certainly 2 plus 2 is not equal to 2. So we see that the algebra of union starts to slightly differ from the algebra of addition. Union has these two rules in common with addition, which, by the way, have names. Let me actually write these names out.
Yes.
This is called commutativity, and this is called associativity. And these are so complicated words that you might not want to remember them, and you don't have to remember them. But in case you were wondering what their names are, these are the names. Commutativity and associativity. And the rule that we just wrote out, which fails for addition, also has a name. It's called idempotency. What happens if I take, I'm now switching to another rule. So what happens if I take A and take its union with the empty set, which we now know is the same as the empty set union with A because of commutativity? It is also A. Yeah, Noluntu here is saying that it should also be A. Everybody agrees with that. If we combine A with nothing, then we will be still left with A. We're not adding anything more to A by taking union with the empty set, right? So that still equals A. This rule, however, is similar to one of the rules for addition. What would that rule be for addition that's similar to this one? Well done, Imi. So it's similar to the rule that x plus 0 equals x. Well, it equals 0 plus x, as we know, but also further than that, it's also equal to x. And that is all the laws that I wanted to share with you. I don't know, Brendan, if you want for us to add anything to that. That concerns union only.
A follow-up to the last one. Does any other set do that? If I combine A with something that's not the empty set, can I still get A?
So here is a very interesting question from Brandon. Is there any set different from the empty set such that, and let's call that set, that hypothetical set, let's call that X. Is there any set X that's different from the empty set, but still has the property that X union with A always equals A for every set A? Can such a set exist? That's the question. For numbers, yeah?
We've had a beautiful response though already.
That's an interesting response, but that's actually true. I agree with that. If X happens to be a subset of A, then X union A will equal A, because by taking the union, we won't be adding any more elements to A because X is already inside A. Let's write this observation down. If X is a subset of A, then X union A will actually equal A. Now, the difference here is that we are requiring this to be true, not just for those A's of which X is a subset, but for every other A as well. So we want this to be true for every A, not just those of which X is a subset. A similar question for numbers would be, is there any number, let's call it small x, different from the number 0, such that x plus A equals A for every number A? And let's first answer this question in the case of numbers. What do you think? Is there a number x? So that no matter what number we add to it, we'll still get that other number back. But that x is not allowed to be 0.
Then A must be 0.
A must be 0. Why must A be 0? Can you explain why?
If A is 0, then we would have x remaining as x.
Ah, we have a very, very interesting answer from the Luntu. Luntu, would you like to? Let me just first switch off the background. So how do you explain that we cannot have such other number x different from 0?
If A is 0, if x cannot be 0, then A must be 0 in order to be maintained as x equals to A. Oh,
You want to add, Amy?
Okay, so if you make A 0, then the leftover whatever number x is will be.
Fantastic. Fantastic. I really like your explanation, Amy. So what we want from this number x is that this number x plus a must equal a for every single a. Let's consider a special case when a is 0, because it must be true for every a. It must also be true in the case when a is 0, right? So if we can then say if such x exists, then we take such x, we add to it 0, it must equal 0. But what do we know about x0? X plus 0. X plus 0 is x, isn't it? So we get x equaling x plus 0 equaling 0. So x is now forced to be 0. But we said x must be different from 0. So it can't be. If there is such x, it must be forced to be 0. It can't be different from 0. It's a contradiction, right?
it's a contradiction.
So this contradicts with the fact that x can't be 0. So since we get a contradiction, it means such x cannot exist. Everybody fine with that?
And intuitively, such an equation feels wrong, right? To say a
Yeah.
plus x equals a, you know, intuitively to increase the size of something and it not increase doesn't feel right. So, you know, instinctively that should have felt like it can't be possible.
So what about the other participants? Are you
Chat.
happy with what we chatted? I see a thumbs up from Ashnil. Sure. Okay, there's another one from Sebastian. And from Ruben. Great. Now that we've established this for numbers, let's go back to our question for sets. And in mathematics, it's very common to use experience from one area and apply it in another area. Can we do something similar with sets? The similar kind of logic that we used here, can we apply that logic for sets? The only question there is what would play the role of 0? Because here we took the special case when a was 0. And for sets, we have a good candidate for 0, which is the empty set.
Yeah.
So what happens if we take the special case when a is the empty set? Then we get x union empty set equals empty set. But what do we know about x union empty set? We've got it here. Anything union with empty set is that thing back. So we get x equals that, and which in turn is equal to the empty set. So in the same way as it worked in the other case, we get here that actually such x cannot exist. It must be empty set if this x is to make the same set with by unioning with another set. I said it in a terrible way now, but it's written on the on the board. Everybody fine with this as well?
So the empty set is special then somehow.
Yes, very special. So thank you very much, Brendan, for this very interesting question. Now that we've established the special property of the empty set, I actually want to go to the other thing that was brought up here, namely that if X is a subset of A, then X union with A must equal A. And you know what I'm wondering about this when I look at this? I'm wondering about the following. Well, first of all, I want to rewrite this in a different way. X is a subset of A, and then the symbol X union A equals A. This symbol stands for implication. It means if the left side is true, then the right side must be true. So the symbol stands for then. And we see this arrow has a direction going from left to right. And I'm wondering whether we can make it go from right to left as well. Is the following true? X union A equaling A, can that give me that X is a subset of A? So in other words, if I have two random sets and I know that X union A equals A, is it then true that X will be a subset of A? We seem to have a comment in the chat, but then the comment was taken back. We did reach our time limit. We did have a half-an-hour interruption, though. I think, though, because of schedules that we might be on, we should probably end here. So this question that I put down here, we're not going to talk about it now. If you have an answer to this question, please send us an email. And the email addresses for this question is going to be exactly the same as for the other one. If you know the answer, and can prove it, it would be good if you can include a proof in your email, an explanation as to why it must be so. Send it to us on these email addresses. So this is one for Brendan, and this other one is for me. All right, then. Shall we end here, Brendan?
I think we should, for the sake of time. Again, apologies for the interruption and the technical issue. This will also, of course, go up on our YouTube channel.
It's the NITheCS YouTube channel, which, in case you're not familiar with, I can send you the link on the chat. Any final questions from the participants? So I've posted in the chat the link to the NITheCS YouTube channel. And here's also the link to the NITheCS website. If you go on this website, then you'll be asked to click for getting a newsletter, and it might be useful because you will be able to get some updates about the activities in the Institute for Theoretical and Computational Sciences. All right then, so let's then say goodbye here, and hope to hope to work with you soon again, and maybe even meet you soon sometime.
All right. Thank you, everyone.
Bye, everyone.
Bye-bye.